Welcome to this explainer. I am so excited you're here today because we're looking at the invisible infrastructure that makes our modern world run. Imagine, just for a second, that every single piece of data on the internet, every email, every streaming video, every text message, is a car. Now think of the internet itself as this massive, sprawling, global network of highways, city streets, and little dirt roads. How on earth do billions of these data cars navigate this insane grid at the exact same time without constantly crashing into dead ends? Well, the answer lies in routing algorithms. Today, we're going to act as digital traffic controllers and break down exactly how these invisible rules classify and direct traffic all across the globe.
Okay, let's dive into this. Here is our roadmap for today. We're going to cover the core rules of digital navigation, compare static versus dynamic routing, break down exactly how dynamic routing calculates paths, explore internal versus external networks, and then we'll wrap up with a few unconventional routing methods.
So, Section 1, the rules of digital navigation and routing rules.
Let's start by defining what these core logic systems actually are. Routing algorithms are essentially the brains inside network routers. They're classified by how they operate, their ultimate purpose, and the specific information they rely on to make their routing decisions. But before we look at the specific types, I really want you to ask yourself a question. What happens when a digital road closes? Say a server completely goes down or a fiber optic cable gets accidentally cut by a construction crew. It happens. So how does the network react to these blockages? Well, network administrators basically have two fundamentally different ways to solve this problem.
That brings us to Section 2, static versus dynamic routing, a routing comparison.
Now, what's really interesting about this is that it's basically the difference between having a printed paper map in your glove box versus using a live traffic app on your smartphone. Notice how clearly the trade-offs are laid out. On the left side, we have static routing. This is your old-school paper map. It involves a human administrator manually configuring the routes on network devices. It's incredibly simple, it has very low overhead on the routers, and quite honestly, it's perfect for small, highly stable networks. But, and this is a really big but, it completely lacks adaptability. If a road closes, static routing doesn't care. It just keeps trying to send data into a brick wall until a human actually intervenes. Now on the right, we have dynamic routing. This is your live traffic app. Routers constantly exchange information and adapt to changes automatically. They're constantly calculating the absolute best paths based on live metrics like hop count, bandwidth, and delay. It is highly scalable and incredibly adaptable, but the cost is much higher overhead on your network equipment.
We can also view this static versus dynamic concept through a slightly different lens. Think of it as adaptive versus non-adaptive routing. Non-adaptive protocols are basically your static routes. They use fixed routes and completely ignore any changes in network conditions. Adaptive routing protocols, on the other hand, are the dynamic ones. They actively adjust their routes the very moment they detect a change in the network environment.
Let's move to Section 3 and see how this builds, how dynamic routing works, and calculating paths. Because dynamic routing is so unbelievably vital for the modern internet, network engineers have developed a few different ways to actually calculate those live routes. The first foundational method we're going to look at is distance vector routing. This algorithm makes decisions based primarily on distance, which it measures in what we call hops. And a hop is exactly what it sounds like. It's simply the trip from one router to the very next. In this system, routers act kind of like gossiping neighbors. They just periodically share their entire routing tables with the routers directly next to them to figure out the shortest path.
A classic example of a distance vector protocol is RIP, or Routing Information Protocol. It is wonderfully simple and it's absolutely great for small networks. However, because these routers only know what their immediate neighbors tell them, this method is famously vulnerable to something called the count to infinity problem. Just imagine your GPS gets confused and directs you into a literal traffic roundabout, and you just keep driving in circles forever and ever because the system literally can't figure out that the exit road is closed. That is exactly what happens to data packets experiencing the count to infinity issue. It's a bit of a nightmare.
So, to solve the limitations of distance vector, we have link state routing. Instead of just asking its neighbors for directions, a link state router gathers information about the actual state and the actual cost of the links across the network. It uses this data to meticulously build a complete big-picture topological map of the entire network right inside its own memory.
So the crucial point here is that by having a full comprehensive map of the network, link state routing is vastly superior for larger networks. A really great example of this is OSPF, or Open Shortest Path First. And yeah, it is significantly more complex to process than distance vector routing, but that complexity totally pays off by providing highly accurate routing decisions for massive enterprise-level environments.
But what if you want the absolute best of both worlds? Well, that brings us to hybrid routing. Just as the name suggests, this algorithm borrows features from both distance vector and link state routing to make its decisions.
Hybrid routing hits the absolute sweet spot. It brilliantly balances the simplicity and lower overhead of distance vector with the accuracy and speed of link state. The standout protocol here is EIGRP, the Enhanced Interior Gateway Routing Protocol, and you will very commonly see this operating inside specific environments, especially Cisco networks.
Moving right along to Section 4, internal versus external networks and network scale.
Now, routing inside a local digital neighborhood is incredibly different from routing out on the massive global internet highway. And this brilliantly illustrates how we categorize that difference into two main buckets. We have IGPs and EGPs. Interior Gateway Protocols, or IGPs, operate purely within a single autonomous system. Think of this like a single university campus or a corporate organization. All those alphabet soup protocols we just learned about, RIP, OSPF, EIGRP, those are all IGPs. On the other hand, we have Exterior Gateway Protocols, or EGPs. These handle the routing between entirely different autonomous systems. So when your organization needs to talk to the wider global internet, it uses an EGP. And the absolute most famous example of that is BGP, the Border Gateway Protocol.
Section 5. Unconventional routing methods and specialized routing.
Standard GPS-style routing is not the only way to move data. Sometimes, network administrators just need to use highly specialized, niche methods to get the job done. One of these methods is routing by flooding. This is the brute force broadcast approach. Let's walk through it. Step 1. A router receives a packet of data. Step 2. It immediately duplicates that packet and shoves it out to absolutely every single neighbor it's connected to except for the one that just sent it. Step 3. The packet rapidly reaches its destination. Now, obviously, it is completely inefficient for a normal network. But in highly specialized environments where routing information is incredibly scarce, this massive broadcast basically guarantees the message gets through.
Another really niche method is source routing. Normally, a packet of data relies on the routers along the way to give it directions, right? But in source routing, the original sender acts like a total dictator. It specifies the exact, complete, turn-by-turn route that the packet must take before it even leaves the station. Because it's so incredibly rigid, it's pretty uncommon in modern networks, but it definitely still exists for very specific troubleshooting and security scenarios.
So, ultimately, why does all of this matter to you as a focused learner? Well, it's because in the real world of cloud computing and network fundamentals, there is simply no single best routing algorithm. These classifications exist because administrators have to choose the right tool for the job. They have to carefully weigh factors like the physical size of the network, the layout or topology, how stable the connections are, and the specific environmental requirements of the business itself. We've seen how simple, static rules and highly complex dynamic maps keep our data flowing today, but I really want to leave you with this final thought. As our digital world grows infinitely larger, with billions of new IoT devices, AI servers, and mobile users coming online every single day, how will our routing algorithms need to evolve next to keep the internet from hitting a dead end? It is absolutely a fascinating problem to ponder. Thanks so much for joining me on this explainer, and keep learning.